Okay, yeah. Hi, everybody, and we are here for the last series of talks for this Spark workshop. Our first speaker, our first speaker is Professor Dhruvoditya Mitra from Nordic Institute for Theoretical Physics, and he's going to speak on using recurrent neural networks to forecast sunspot cycle 25. So, Professor, please take over.
Thanks very much. Actually, I believe I am the first and the only speaker,
Uh,
right?
no, we have Paul and Shaumitra
Okay,
after you speak.
okay,
Yeah.
okay, okay, good. So I will not be able to say the last word in the whole conference. Okay, so it has been a long day and maybe I will be able to keep it short, shorter than usual, but only if I am able to share my screen. So this, okay. So can you see my screen? How about now?
No,
No?
not yet.
Okay.
Are you sharing your entire screen?
No, one window.
Don't do
How
that,
about
Dhruvo. Share your
Yeah.
entire screen. Yeah, now it's
share my
working.
entire screen?
Yeah.
Now
Now
it's
it's coming
working.
up. Yeah. Yeah.
Okay,
I can
fine.
see it.
Fine. Okay, excellent. So I'm going to speak to a screen. Hi, thanks very much. This has been a very nice meeting so far, and this is the end. So it has been a very nice meeting all the time. I am particularly grateful to the LOC who has worked wonderfully, Shubhadeep, Prashenjit, and the others, who has made it a really enjoyable meeting. I will talk about uh, sunspots. And normally, when I gave this talk before to engineers, for example, or statistical physicists, what I noticed, I had to tell them about what a sunspot is, how it starts with Galileo, and so on. To this audience, that's kind of a waste of time. So I will try to go over it quickly, and I will spend some time trying to tell you about the technique. And I will try to tell you about the technique as simply as possible. So as you recognize on the screen, there is Galileo and the sun. And the sun, you can see there is a sunspot. There are actually sunspots that the arrows are pointing out, but they are hardly visible. So you change the scale and then you see something. So these sunspots, they are places of very strong magnetic field. What you see here are actually active regions. So that there is black and white. These are the two polarities. These images are from 15th March 2011. If you look today, well, there may be a spot, there may not be a spot. So the source of the images you can find here is called Sun Today. Uh, Now the sunspots are connected to the space weather. So here we have had a long discussion about what space weather is and so on. So I'm not going to spend time talking about that. Everyone knows what we are talking about. Now there is some connection between the sunspots and the space weather. So as you know that the sunspots go on an 11-year cycle. Actually, it's a 22-year cycle, but that doesn't matter for our purpose. We will just think of it like an 11-year cycle. On top of that, you know that cycles are not really very well periodic. Sometimes the amplitudes are larger, sometimes they are smaller. There are times when some cycles are simply missing. These are called Maunder minima. Now, when the sunspot cycle is stronger, you typically get more solar storms. That's how kind of the space weather is connected to the sunspot cycle. So for example, before a sunspot cycle starts, you may want to know, is this cycle going to be a typical cycle? Or is it going to be one of those cycles where you have a very strong magnetic field? Or is it going to be a cycle which is much weaker than the other ones? The Bendu is someone who has worked a lot on this. There are many other groups who has worked on this. This is one of the things that people in various dynamo models study. That's another discussion. I am not going to get into that. Here we are going to use something called a recurrent neural network to see, to be able to capture such a thing. Any questions so far? Can you still hear me?
Yes, we can hear you. There are no
Yes.
questions in
Okay.
the chat box.
Good. Good. Excellent. So this is sunspots over time. So I guess a lot of you have seen this picture before. And this picture only goes down back to 1600s. You can see the Maunder minima. The now what we know and what we believe is that the solar magnetic activity is determined by turbulence inside the sun. Inside the sun, from about zero point 0.7 solar radius to the outside the solar surface, it's a plasma, and that's a plasma that is convectively turbulent. And it is this turbulence that creates sunspots, among many other things. So it's a solution of the magnetohydrodynamic equations. So it's a very, very difficult problem to solve. But when we are talking about forecasting something, we should take the lesson from the best forecast system we have at the moment, which is weather forecast. So here I would like to make a distinction about between two things. So we tend to use the words predict and forecast almost interchangeably. I would suggest the following. So for example, in physics, when you say Dirac's equation predicted the positron, that has no statistical element in it. So that for that, I will try to use the word prediction. Whereas when we say tomorrow there is 60% chance of rain, that's what I would call a forecast. So what we are trying to make here is a forecast. And then I will like to draw an analogy, for example, between climate and, on one hand, climate and weather, on the other hand, space weather, and a very long time behavior, for example, of sunspots. So at the moment, what we are trying to see is what happens in the next cycle, which is kind of the question if you ask, is the next rainy season going to be have is the next monsoon going to be much more stronger than this monsoon, or is it going to be an average monsoon? As you know that the weather prediction and the climate prediction groups have done a wonderful job. And of course, weather prediction is slightly bit tricky in the tropics. It's easier in the higher latitude. Even then, couple of days, a prediction which is, or a forecast which is forecasting 2 days ahead is reasonably accurate. The way they do this is that they actually solve the equations the best way they know. I guess this community knows quite a lot about how weather forecasting is done. So I will just say very few words about it. On one hand, you try to solve for the equations of weather as you know it the best, with parameters as you know them the best, equation of state and so on. And at the same time, you have observations coming from lots of weather stations. So you start with an initial condition which you think is the best fit to the observation at the moment, go ahead by computing by a small amount, and now you remember and you know already that this is a chaotic system. So if you have a very small difference from where you started, you will actually go a long distance away and your forecast will be completely useless. This is the whole point of the famous Lorentz butterfly, where he says that the fluttering of wings of a butterfly may be responsible for a storm long, long time later. So if that is the case, you may think that forecasting such a system is utterly useless. It's an impossible task. So the idea here is that you evolve your system and maybe you are going slightly away from what the actual system is. But you have got your next set of data now. So try to take that into account so that you are now nudged into the right direction again. So you evolve when you correct, and you evolve when you correct, and you correct always in something of a least square sense. This is in a way what is called data assimilation. Here we are going to use something different because we don't have a very good model to solve this problem. The magnetohydrodynamic equations for the sun with the right parameters is impossible to solve in any computer that we have at the moment. When we solve the MHD equations in a computer, we have a Reynolds and magnetic Reynolds number, which corresponds to something like solving sun with honey inside it. So being far away, we are now going to completely forget the equations and try to model them by much more abstract things. But before that, before we actually go and try to model the data, it's a good idea to try to see how we do a job with a system, with a model system. Because you see, if you look at the data, you go back a certain number of cycles and that's it. The data is limited. Whereas if you apply these equations to a model, you can run the model as long as you wish and get as good a forecast as you want to, if it is at all possible. So we start with a model. This is a model that Dibendu and one of his students wrote down some point back. For those who are somewhat familiar with Dynamo, this is not a strange model. So when you try to describe the magnetic field in a dynamo, you often start with the magnetic field B and the vector potential A. Both of them are the toroidal components or the phi components. So look at the top left equation, look at the equation of dB dt, and you find that it has one term where B basically decays over a time scale tau. Was there a question?
Yes, we do have a question from
Yes.
Sarkot. Uh, if we know the MHD equations with the right parameters, then can we model the true time series pretty well? I understand that finding those parameters is tough.
We can't solve the MHD equations with the right parameters in any computer we have now. That's just, you need a computer too large to do that problem. Was that was that the answer? Well, how do I know? Shoikav, is that okay?
Um,
Okay. Okay, let me go ahead.
yeah.
So the other thing
Uh,
to notice here, yes,
he
was there a
asks,
question?
he asks if we knew the parameters, then what would have happened? Yeah.
Then we would, we kind of know, I mean, we have reasonable estimate, although not very accurate. We have some reasonable estimate of the parameters. That's not the point here. The point is that we can't solve the PDEs with those parameters. That would require a resolution that is way too large than anything we can do at the moment. Okay. And is there a response?
Yeah, he says, okay, I think, yeah,
Okay.
I think you can
Okay.
proceed.
Let's go ahead. So the other thing to notice about this equation is that the magnetic field depends on A at some time back. So this is what is called a delay differential equation. The right hand side of the equation depends on, it's a memory term, it depends on something that happened a certain time back. So that's the equation for the B, and the equation for A, you have a term that is alpha. So this models the famous alpha effect, and the alpha effect here is taken to be stochastic. See, alpha is some constant alpha 0 plus a term sigma, which is random in time. So this is the quantity that actually gives you the stochastic behavior in the time series that you see here. So here you see a time series which is supposed to be a model of the number of sunspot. You see that there is a kind of a periodic behavior, but not every period is of the same length and not every period is of the same amplitude. This is not a very bad picture of sunspot activity. And this is the first thing we will start with. We will start by trying to model it with something called an echo state network. So I'll spend a little bit of time trying to explain this to you. And please ask any question that you may have. So the echo state network is also often called a reservoir. It's the physicists who call this thing reservoir computing. And the idea is kind of the following. Inside that blue circle, what you have is a very large matrix. And now to think of it as a matrix, you first think of it as certain number of nodes. The number of nodes are these blue dots here that we show in this picture. And then you see the dots are connected to each other. So a connection of a dot with itself is like a diagonal term in the matrix. And the connection of a dot with some other dot is a corresponding off-diagonal term in the matrix. And you realize this is a matrix where the connection between node 1 and node 5 may have a certain strength. But the connection between node 5 and node 1 may have a different strength. So you can have, this is not a symmetric matrix, your off-diagonal terms can be different. And this matrix is typically random, but it is constructed with certain constraints. For example, it is constructed with the constraint that if you look at its spectral radius, it's all the eigenvalues are actually less than 1. This is for the reason of stability. So this matrix, which is a very large and sparse matrix, it has lots of zeros on various parts of the matrix. It's random, it's sparse, it's large. This is what is called the reservoir. Outside the reservoir, there are three different nodes. One is called an input neuron, one is called a feedback neuron, and one is called an output neuron. The names come from history and they can be somewhat little bit misleading. So the input neuron has a signal U in, which is typically constant. And this neuron is coupled to every neuron in the reservoir with a random weight, which is W in. The feedback neuron is actually where the number of sunspots as a function of time, for example, is going to be fed. Okay. The idea is that in the feedback neuron, you feed a time series. And as you feed it to the time series, the reservoir kind of computes and you start getting an output. Okay. The output has connections to every neuron, and these connections are W out, the weight of these connections, and the feedback is WFB. What you do in the beginning is you set up this random reservoir, and it is not going to change over the evolution of your equations. That thing is going to be remain the same. The W in, the weights that you choose from the input neuron, they are also constant. The weights that couple to the feedback neuron is also typically constant. But the weights that are coupled to the output neuron, these are the ones that you are going to optimize. These are the ones that you are going to change to do the following thing. So as you know, any of these problems, you have to have a cost function. So the idea is kind of think of this whole reservoir as some kind of a huge machine. And to that machine, you are giving your input signal, say one data point at a time. So you give it one data point, you get an output. You give another data point, you get another output. So the input signal is being converted into an output signal. The idea is the machine should work in a way so that it actually mimics what is being fed in the input. Okay. So the output one, which is the thing here, is Y. I'm sorry, the output is Y hat, and the input is input, which is actually the signal that we are putting in the feedback neuron, is Y. And you subtract them and take the mod square, and that is your cost function. That is the function that you are going to minimize. But there is also, it multiplies by some beta, and then the quantity that you are trying to change, the W out, it also has its L square norm. Why do we do that? Actually your cost function is the first one. But what you want to do is you don't want to over optimize the problem. So for that, you add some kind of a correction. This is often called a regularization term. And then you minimize this cost function to optimize by changing the W outs. So the idea now is you have a very long time series, and you take the time series and divide it in two parts. There is a training part and a testing part. Over the training part, you try to use this and train it as much as possible, and you get the set of W outs by which, and once the training part is over, you would say that my machine has learned the input. And then evolve the machine further. So, and when you evolve the machine further, I'm sorry, in this second stage, you take your output and feed it back to the feedback. So that's why I guess it's called a feedback. Once you do that, your machine is giving a time series. And now you see if the time series, how close it is to the actual time series. This time series is your forecast. The important thing here is every node has a variable x, which is evolving, and it evolves, which is influenced by the WU in, which is the signal at the input neuron, which is basically a constant, and the weights W in. And these are the weights of the reservoir and the weight from the feedback. That's how the evolution of every point goes. The crucial thing is the tan hyperbolic function here. So you need a nonlinear function of similar type to make the whole problem work. It is also something which makes the analysis of the problem more difficult, but that's not the question here at the moment. So
If I may interrupt, there's a
absolutely,
question from there's a question from Shomitsruda. He's asking, what should be the input here? Like feedback neuron is the sunspot cycle. Is it
absolutely,
kind of
yes.
data assimilation?
See, when you do a data assimilation, then you're in place of this machine, you would have the actual equations, and you will be learning parameters in the equation. So this is not, that's why this is not data assimilation. This network, for example, is agnostic of what kind of equation you are trying to solve. This can learn a whole class of many equations. Was that clear?
He says yes. Okay, I think you can
Excellent.
go ahead.
Another question? No. Okay. So here
One
is the,
thing,
absolutely.
what is the input?
Input is some constant number here.
Okay.
This is strange nomenclature, I agree. But that's what they do. Not my fault. I didn't invent it.
Okay. That's-
Okay. So now I am with the data that I showed you before, I am going to explain exactly what we do. So over at the top, what we obtain from the equation, and then you see the dashed line, that's when we stop the training. And that's when in the bottom left, you can see the red line. So there is 1 cycle, 2 cycle, 3 cycle, and 4 cycles. So the red line is the actual data, and the blue line is the forecast that comes from our machine. As you see, after 1 cycle, the forecast and the actual data have actually departed quite a lot from each other. This did not change irrespective of how far back we went in time. So the first lesson to learn is that this technique at the moment is unable to forecast anything beyond 1 cycle. So that's the first lesson we learn from this. Now, before I go ahead, I will explain a little bit exactly what we mean here. So you see this green line and you see a yellow band around it. So what we want to do and what you should always do when you are forecasting, you should not only forecast, but you should always set an error bar on your forecast. You can't just say tomorrow there is going to be rain. You have to say what percentage is the probability of rain. And this system is a very good one to be able to do that. What you do is, you see, you can choose many reservoirs, each one with an initial random set of connections. Each of these is perfectly equivalent. So what you have is an ensemble of reservoirs, and you train all of them. And the blue one is the mean of their forecast, and the red and the yellow band is the variance of their forecast. So now look at bottom right corner, and here we look carefully at just one cycle. You see that during the rising phase, the forecast is actually quite good, and then it slightly departs, and the red line and the blue line are slightly away from each other. I will show you a little bit later. It matters quite a lot where you stop your learning and start forecasting. But
Uh,
by that, what I mean is whether you do it at the end of a cycle or in the middle of a cycle or at the top of a cycle. Yes, please.
yes, there is a question from Debesh Bhattacharjee. He's asking why this model assumes constant weights for the input and feedback channels while the output weight varies.
I don't know why. That's kind of how the model is constructed. There can be many variations of it, but you can vary the weights in many places, but more you have, more difficult the problem becomes. You also realize that when you look at the weights of the reservoir itself, they all it has to be such that the eigenvalue of the reservoir, all the eigenvalues must be less than 1. Otherwise, you will not have a stable problem. So that is not a very easy thing to do if you start changing all of them and trying to fit your data. Was that even a partially satisfactory answer?
Dhruvo,
Shall
I
I
think
go
you should
ahead?
assume that there is no confusion
Okay,
and proceed
and
unless
proceed.
somebody asks, a question.
Okay, so now I'm going to show you what the results are. So far I talked about this echo state network, but this belongs to a whole class of what are called recurrent neural networks. All of their job, for the main purpose of their existence, is to actually forecast time series. We have used several of them, some of them quite fancy, and I am not going to describe how they work. I have described the one that turned out to work the best. But here I am going to show you what happens with all of them. So on the left is the cycle 22, and on the right is the cycle 23. What you have as the solar data is actually a windowed average of the solar data. Okay, keep that in mind. It will come back, it will become important at some point. So the green dots are what we call the modified ESN. So what I have described to you is the echo state network ESN, and we are going to modify it. And I'm going to tell you a little bit later how we modify it. But let's see what's the best it can do. The blue triangle is the linear autoregression, which is the simplest thing you could do. The upside down black triangle is what is called vanilla recurrent neural network. And there are two other ones. One is called LSTM and the other is called GRU. I have forgotten what the acronyms mean, and I'm not going to discuss them at the moment. It will take too long. Maybe you should bother Shodangshu and Shoikat about them. So if you look at this on cycle 22, the data has a typical two-peak kind of structure, and you have the echo state network, the blue one, and what we show here is the mean. You remember we have a mean and a variance on the forecast. I'm not showing the variance at the moment. I will show that later. And then you see that Auto degradation is doing the worst. It basically has kind of a peak and practically disconnected with the sunspots. And the LSTM and Groove, which are actually computationally much more intensive, they need more computational resources than the ESN, hasn't done such a good job. And it is actually the ESN, the modified ESN, that hasn't done such a bad job. If you look at cycle 23, you again see that the ESN is the one that has done the best job. So now let me talk about the minor modification that we do. So what I told you before was that you take the data at one point at a time and you make your forecast one point at a time. What you can do, you can take several input points at different times and think of that as an input vector. So you can say, I am not going to absorb the data one point at a time and forecast one point at a time. I am going to take P points at a time and forecast Q points at a time. Both one being a P-dimensional vector and the other being a Q-dimensional vector. This change actually improves things quite a lot. So on the top is the standard ESN, and on the bottom is the ESN as we have modified it. There is cycle 23, cycle 24, and cycle 25, which is the cycle to come, or it has already arrived. So let me discuss this picture for the moment. In the top one, you see the red data, which is the actual data. And I remember I told you it's a windowed average. So this is the average, and the shaded blue part is the variance. So that you could see is the error on the data itself. And then you have the green line, which is the mean of our forecast, and then there is a band around it. So essentially, more overlap is there between the yellow band and the, well, bluish band, the better it is. So cycle 23 is kind of okay. Cycle 24, it's actually somewhat better. But now, after we have changed the trick, after we have included this, one important thing has happened. The error in our forecast has significantly decreased. And now you see it actually in cycle 23 fits quite well with the data. And in cycle 24, well, not too bad either. So there is distinct advantage in using the modified ESN. Now have a look at the forecast for cycle 25 with both of these. So the upper one has a much bigger error than the lower one. So we would think that the lower one, which is the modified ESN, is the method that you should trust in this problem. I told you I will tell you about what happens. It depends crucially on when we stop training. And this is on the left. What we do is we stop training at different points. So as you see in the top left, we stopped training a little bit before 2008. Then top right, we stopped training at 2008. And then we stopped training at 2010 and a little bit later 2010. So the trick, the reason it is being done here is, see, one thing is, the whole idea is you need to know the cycle before the cycle starts. So you need to kind of try to play around with what is happening near the end of one cycle. And near the end of one cycle, there can be several cases. One is before the cycle has actually started, you are in the end of the previous cycle. Then at the minima of the cycle, then at the rising phase, and then when the cycle has actually progressed a little bit. So as you can see, the best forecast actually comes when your cycle has actually progressed a little bit. So it's a good idea not to try to forecast exactly at the minima of the cycle, but to wait maybe a couple of years and to then try to do the forecast again. Now, this paper that from which the data I'm showing you was actually has been in the archive for more than a couple of years now. That has another story, and that has to do with the stupidity of the editors of A and A. but this is not the place to criticize them because I believe none of them are listening to this. So, but it gave us the opportunity to actually do this experiment with the real data. So over on the
Dhruvo,
here
I
on the
think
right,
one important thing that should be highlighted here, and I think which you probably forgot to mention, unless I was not paying attention closely, is that the only time series that is being utilized to train the model is the toroidal field time series.
for the model, yes, here we are in the sunspot data.
I know, but one has to make it clear that the model is trained only based on the toroidal field time series, not on both the toroidal field and the poloidal field time series. So it is not
By
surprising,
the
in fact, for those who understand solar dynamos, that your prediction becomes a little better if you allow the next cycle to progress
Oh, I
because
see what you mean. I see
you're
what you mean.
building
I
in the
see what you
Weimar
mean.
effect
I
in the
see
toroidal
what you
field.
mean. That's one way of thinking about it, absolutely. But it it's kind of it's also you can think of it as a generic property of any time series because you see when you are at the minima, then you have the least information content in your signal. Your signal to noise ratio is the largest. And when you are in the previous cycle, then those information will actually, whatever information you are putting may actually get lost as you go down. So absolutely right. But there is also the other issue. This is the usual way you think about it, but it doesn't completely work here. Because if you look at the data here, you also see that your error of the observation actually changes with the observation itself. So that's a little bit tricky problem to address. Coming back, uh, what you see is the blue line, I'm sorry, the yellow line. And this was the forecast being done around 2010. And now we have progressed a little bit further. We know the data better. And we start and make another forecast from the green lines. And you see the difference between the two. And I will tend to believe the green one more than the yellow one. So this is final forecast for the cycle 25, where we have put everything together. So all the different algorithms that we have used, we have also used them in an ensemble manner and put errors on them, except the linear auto-regression, which always does a bad job, and we didn't really try to play anything fancy with it. So you see that the forecast of the modified ESN, which is the green one, is one way. Several other forecasts are slightly higher, and the cycle falls off at a slightly faster rate. Well, the rate is kind of the same, but the number of sunspots remains somewhat higher. So there is the modified ESN that I believe that I think is the best one. So we reach the end. As you know, this is the saying that is attributed to Niels Bohr. The main lesson you learn is prediction is very difficult, especially about the future. We use 5 different recurrent neural network algorithms. ESN works the best, and the end result is the following. So from the data until 2021, both the algorithms agree on the following point. Cycle 25 is going to last for about 10 years. In one case, the peak is going to be in July 2024, and the other case, the peak is going to be in October 2024. But I would not put, I, I don't have a lot of confidence on those data itself because there are some errors on them. And as you see from the plots, they are on a 10-year scale. So months look too short. I mean, if you zoomed in, you would see that the error is much bigger than months. The maximum sunspots in one algorithm is 108, the other one is 104, one is plus minus 1, other plus minus 14. So they're basically agrees with each other within error bars. That's all at the moment. This is basically was a fun game to play where we learned something about the ecostate network, how to use it and so on, and make a new forecast for the upcoming solar cycle. So I don't actually remember how well this forecast matches or does not match with the model-based forecast. But over here again, see when two fields try to work together, for example, machine learning and astrophysics, you often find conflicts in nomenclature. So when we say model, we typically mean a differential equation or a partial differential equation that models some physical phenomena. And when I say algorithm, I mean a particular machine learning technique. Whereas for the machine learning practitioners, a model is a particular machine learning technique. So this creates utter confusions when the communities try to talk with each other. Thanks very much. I will take the questions now.
Thank you so much, Professor Trivaditya. That was a very, very nice talk. We have a question from Jesneel. He asks, the model predictions for training stopped beyond 2010. Uh, look slightly worse off than the ones that stopped at 2010. Now, intuitively, it would seem that training for a longer time would mean that we have more information to work with and make better predictions, but it doesn't seem to play out as expected in reality.
Uh,
Why is this?
that's absolutely true. But you see, okay, let me see. I believe you mean these plots, right? See, in the time scale of things, you are actually gaining very little in training. It's just 2 years, right? So given that you have looked at many cycles before, just 2 years data is not going to really change anything. If it is that sensitive to the results that you are looking at, then it is already too sensitive to make a meaningful result. Jasnil, is that a kind of a acceptable explanation?
Um, I guess to an extent, yes, but then it still doesn't answer my question as to why the model at the bottom right corner is much worse off than the one on the bottom left.
Bottom right, is it much worse off?
I mean, it seems to get the amplitude of the wave more poorly than the one on the bottom left.
That is true. But on average, I don't know if that is much worse off. I would think that if you look at the bottom left, you see there is a big gap over a long time. You see the thing that you are minimizing is not the value at the peak. You, do you see what I mean? See, you may choose to tune the model to optimize certain behavior. But what we have tried to do is the least square error over a large length of time. That doesn't make sure that it's the peaks that it is going to pick up the best. If it is the peak that you want it to pick up the best, you can change the algorithm somewhat to put more weight into the time series when the peak appears. That's also some trick you can play with.
Oh, okay. Okay, that makes sense. All right. Thank you.
But before you play any of those tricks, ask Shoikot and Shorangshu. Anything else?
Okay, we have another
So, I mean,
question.
okay, go ahead, go ahead.
Yeah, we have another question from Ashwin. He asks, I wonder how we are predicting the upcoming forecast with the ending of one solar cycle, since there are many types of solar cycles itself, like Maunder Minima and many other unknown solar cycles.
You mean that there is the 11-year cycle and there are also many other longer timescale cycles in the sun? Is that what you mean?
Yes.
See, as far as the data is concerned, it doesn't care about the physics of those different cycles. This is a very crude way of understanding physics. There's really very little here to give a physical interpretation. This is so I would not like to get into the story of many cycles here. So if, for example, if the next cycle was a Maunder minima in reality, then would the algorithm have picked it up? Most likely somewhat, yes. We have tried such things with synthetic data. But how would it pick it up? I don't know. I really don't know. Was that some answer? So how much time do we have?
Actually, we don't. We need to move on
Okay.
to the next
So
talk.
maybe I will just take Dibendu's last question.
Yes.
Dibendu, you were saying something or a comment, is it?
Yes, so I have more of a comment because I'm a co-author on this, because it's not very much as this. Um, uh, I'm still a bit worried about one aspect of this work that I still don't understand very well, which is that how good when we're trying to mimic the solar cycle with a
Right.
model. By model, I mean the time delay model on which we are training a machine learning algorithm and then applying it on real solar data. Now, of course,
But see, we're not using the trained values for the model on the solar data.
I know, but I'm saying that the
Right.
model is, we are identifying the best model to make the prediction based on the time delay model that we have, right?
You mean among the various machine learning algorithms, the GRU
Yes.
and LSTM? That's true.
Yes.
Yes.
Right. Um, Now, so this is going to be somewhat dependent on how good a model to begin with is a time delay model for the solar cycle.
That's very much true.
Yeah. So one aspect of this model which concerns me a little bit is this issue of the Waldmeier effect. How well do we capture it? Particularly the fact that stronger cycles tend to be shorter and rise to the peak in a much shorter period of time. Uh, that remains as a concern. We can discuss this later, I think, after the meeting.
Right.
So I still am a bit concerned, and that's why I think we're still waiting to kind of really submit this paper. Is that how does this translate from a toy model to the actual sun? Is what really still concerns me about this particular
I
model,
think I think it should bother us.
and we should worry about that a little bit. I think. Uh,
Right. We
yeah,
should. So thanks
that's more
very
of a
much.
comment, but I think this is something that we need to work upon.
Yes, this is something that we need to think about next week.
Yeah. Yeah.
So thanks very much to the organizers. And I will stop the screen sharing now.
Thank you so much, Professor Mitra. Moving on. Yeah,
Stop.
yeah. Okay. For the next talk, we have Dr. Paul Wright from HEPL, Stanford University, and he would talk on a machine learning data set with SDO observations.
Thank you. I'm just trying to figure out. Okay, I think you can see my screen.
Yes, we can.
So yeah, 1 second. Losing everything. Awesome. Yeah, so I'm Paul. I'm currently working alongside Spaceml, actually, as a curator and researcher. And this is kind of where we're generating this SGML data set. So in this talk, I'm going to introduce the Solar Dynamics Observatory that many of you will be familiar with, and I expect that this is going to be very high level, sorry. And I will also discuss the Solar Dynamics Observatory machine learning dataset, and specifically SGML on Spaceml. So to give you an outline of this talk, the first half will be concentrating on the SGML dataset, and then the second half will talk about Spaceml, the SGML notebook demo, and a few projects that use the SGML dataset. So before we dive in, I want to take the time to quickly summarize the main points of this talk. So as we know, SGO has 3 instruments, each observe the sun over varying wavelengths and at varying cadences. SGO has obtained over 500 million images. This is a petabyte scale dataset ideal for computer vision and machine learning applications. However, while SGO data are easily accessible, pre-processing these for scientific analysis often requires specialized heliophysics knowledge. So while it is accessible, we want to address this. So we've created SGML. This is a cleaned, curated dataset covering the entirety of the SGO mission. Spaceml brings together data storage on Google Cloud, compute on the Colab Google Cloud platform, and well-commented version control notebooks for easy data access and reproducibility. So before I get into the SGML dataset, I'd like to introduce SDO. So I expect most people here will already know the information that I'll present, but as it's being recorded, I think, I thought it'd be best just to leave this in case someone isn't aware. So STO observes the sun from the visible solar surface up to the diffuse hot solar corona. We'll start the photosphere, and this is with data obtained by the helioseismic and magnetic imager. So as we can see, as we can see, and as we know, in this movie, at this resolution, sunspots appear to cross a featureless surface, but we know that at smaller scales, there's granulation present due to convection cells. This highlights an important point of this data and the sun itself, and that features across a wide range of scales, both in the terms of their lifetime and in their physical size. And this becomes a problem when trying to create a standardized data set for heliophysics research. So while we know, so to talk more about the features across a wide range of scales, while we know sunspot groups can persist for many weeks, these convection cells last tens of minutes. So depending on your use case, you may require different resolution and different cadences of STO data. In addition to observing the photosphere, HMI also produces maps of the sun's magnetic field, and shown to the right is the line of sight component derived from the full vector field. The milligrams are derived every, I think, 45 seconds or 12 minutes at 4K by 4K. So moving on from HMI, the second instrument on STO is the atmospheric imaging assembly. We observe the solar corona over 10 channels ranging from 5,000 to 6 million Kelvin. And here we show the 171 angstrom channel. This is approximately centered at 0.6 million Kelvin. And the data obtained at much higher cadence than HMI with one image every 12 seconds. As we know, the corona was filled with unresolved high temperature loops. This is kind of showing that the features, the corona, so as we know, the corona is filled with like unresolved high temperature loops. And these are connecting regions of opposite polarity, as we showed in the HMI data. And these features occur across a wide range of scales, as you can see here. So from the four videos of these two instruments, there are clearly some artifacts that you've noticed. I wasn't just showing these videos for the sake of it. They show 4 different problems. The exposure time is variable. So when there is a solar flare, the exposure time does decrease. Telescope jitter is present, so you can see that the sun occasionally moves in these images. Eclipses occur, so the sun gets eclipsed by planetary bodies, and the full sun, as you can see in here, the full sun occasionally dims in these images. So the third and final instrument on STO is the extreme ultraviolet variability experiment. STO Eve provides sun as a star observations of the extreme ultraviolet every 10 seconds. As shown on the right, Eve observes a solar spectral irradiance from 5 to 110 nanometers. But unfortunately, the MEGS-A component that overlapped the red bands that correspond to the STO AIA bands ceased to operate in 2014. I'll talk more about an ML solution to this later. But essentially, what we have is 3 instruments, 2 that obtain images, and 1 that obtains sun's star time series. So over the last decade, STO has enabled countless advancements in our understanding of our closest star. There is incredible potential for statistical machine learning approaches. And while it's generally advisable to leave data corrections to the user, this pre-processing may act as an unnecessary hurdle for those wishing to experiment. So to address the issues mentioned, we have present the SJML dataset. So the SJML dataset includes data processing such as rotating images to solar north, co-alignment of images taken at the same time, correction of the Earth's elliptical orbit around the sun, and correction for AIA degradation. This degradation correction is required as EV filters are known to degrade in orbit, which reduces the apparent brightness of the sun over time. The final image data is provided at 512 by 512 and either 6-minute or 12-minute cadence. As discussed, we know that the sun has features on a wide range of time and spatial scales. We picked a resolution that's satisfactory for the work that we were doing that I'll discuss later. And this was now casting essentially Eve solar spectral irradiance from AIA images, but it also limits the size of the data set. This is 7 terabytes in version 1 at 512 by 512. If you require higher resolution data, the code to generate this is online, but we didn't want to start uploading petabytes of data to the Google Cloud.
So can I ask something?
Yes.
What do you exactly mean by UV filters degrade in orbit? I didn't really understand.
So So the filters that are used on SDO to take images like this, they, in the presence of extreme ultraviolet, they degrade such that they let less light through. Later on, I will show a machine learning example where we try and also correct this degradation, but I think it'll make it apparently clear how the apparent brightness of the sun dims over time due to essentially exposing these filters to EUV. Does that answer your question?
Okay, yeah. Thank you.
I'll show you and I'll point it out when it happens. But basically, so the 2019 paper of this is version 1 of the Sjml data set, and we learned a lot from this. We originally only had 2010 to 2018 and at a size of 7 terabytes. We stored this as NumPy arrays on the Stanford Digital Repository, but there were a number of issues with this. The data is stored away from appropriate computing resources. Download is required. I personally don't have 7 terabytes of space on my local machine. And essentially, the size of the data is prohibitive, right? There were no demonstration notebooks available. And importantly, there was no metadata associated with these images. One of the great things about scientific data from SDO is that you have both the images and metadata information. So what we've done is we've generated version 2, and we call this SDOML on Spaceml. So we've hosted this on spaceml.org, which I'll discuss in a bit. But importantly, it goes from 2010 to present. It is stored as ZAR arrays, so this includes the image and metadata. And this is freely available on Google Cloud. So small data set, you can freely accessible through the Google Cloud platform, and complete data access is available on request. The important thing here is that we're not asking anyone to download the data. We think that the best way of performing this research is to use the Colab, something like the free Colab platform, to access the data and perform everything on the cloud. We've also updated the degradation curves. These degradation curves are essentially corrected every few years now. Now that the MEGZ component has gone, they're corrected every few years. And this is to account for that dimming that I mentioned. So as I mentioned, if you put an EUV filter up in space to detect the EUV emission, it generally degrades over time, letting less light through as the instrument ages. So that is corrected based on the latest correction tables, and we've included that in the metadata so you can reverse it if that's something that you'd like to do. We also have provisions in place to continually update and version this data, and the code is available at sjml.org. We would like to generate the corrected data. Well, we would like you to use the data that's on the cloud as it's free, but if you'd like to generate corrected data at your appropriate timescales and resolutions, you're very welcome to, and the code is there for that. So before I demonstrate SDOML data access, I wanted to introduce Spaceml and how you'd navigate to the notebooks. So Spaceml is an open source, free project, and there's a machine learning toolbox and developer community building open science AI applications for space science and exploration. We host a number of freely accessible data sets for scientific analysis, including SDOML, and there are project pages that demonstrate the published results with reproducible notebooks. So this is trying to bring together storage, code, and compute all in one place to allow people to easily reproduce and use our data sets. So if we go to the Spaceml website, you'll be greeted with a number of projects. Clicking through to the SDOML project leads you to kind of an overview, a link to the data sets, a link to the interactive notebook, and to the notebook code in GitHub or GitLab, depending on where we have stored it. So in the following slides, I'll walk you through a pared down version of this notebook so you understand how you can load this data, how you can plot it, and even use SumPy maps. So we've already gone over the introductory material, and we'll start essentially halfway down this notebook. We install here ZAR. So this is just how the data is stored. It's stored as chunked, compressed, and dimensional arrays. SunPy, because we want to demonstrate how in version 2, we can now create a SunPy map object. And GCSFS, which is a way of interacting with Google Cloud Storage. Here we also utilize Dask, an open source library for parallel computing. So in cell 3, we provide the location of the small subset of the dataset from August 2010. This example concentrates on AIA. The process is very similar for the other instruments, such as HMI and Eve. To access this data, in cell 4, we first instantiate a ZAR group. And in cell 5, we then can just visualize how the data is stored. From the hierarchy, we see that it's stored per year and per wavelength channel. So for example, we have August 2010 here in this small demo data set. It consists of 6,000 512 by 512 images stored as float 32. We can, so as we know the structure from the hierarchy, we can easily access this. So we just ask for 2010, 171 angstroms. And from here, we load it as a Dask array, but it can just be manipulated as a NumPy. As a slight aside, to highlight how Dask is working, essentially, this visualizes how the data is stored. So it's a 6 GB array stored in 52 chunks of 125 megabytes. So for those of us that want to use the data as is and don't really care about the metadata, we can just index the Dask array, just like with NumPy, and plot as usual. In this cell, we select the 6,000th image. We extract the color map from SunPy. We square root the data due to the large dynamic range, and then we just plot it. So that's how you can just quickly load some data on the fly. As version 2 of the SJML contains header information, which we didn't have previously, we can also select a subset of this data using one of the keywords. Here's a very simple example using exposure time. But in cell 9, we essentially just extract the exposure times from our array and then plot them. So what we see is that this does vary over time. And we may even want to then subsample our Dask array using exposure time. So we use indexes where the exposure time is less than 2 seconds, and then we just select those images. And now the selected images is 4.2 gigabytes versus the original 6 and 4,000 entries versus the original 6,000. So the really cool bit, and I think here is important for heliophysicists, is that if you want to integrate SJML into your normal workflow, you may want to manipulate the data with SunPy. So SunPy is the open source library for solar physics analysis. And as we contain header information, we can just extract the data and the fits header as a dictionary, as in cell 13, create the SunPy map, as in cell 14, and finally in cell 15, we can plot the image. Note here that the axes are now in physical units and the observation data is included. So this is a quick introduction to how to load the SJML dataset. And I'd recommend visiting spaceml.org where you can get the full notebook that looks at HMI. In the second part of this talk, I'd like to discuss a few projects that use the SJML dataset. I'll start with an overview of the AIA auto-calibration method before going in depth into DPM, which is a method for getting the temperature distribution of the solar atmosphere. And after this, I'll briefly touch on our plans for the EV virtual instrument and in the future. So if we navigate back to the Spaceml webpage, we can see a number of project cards. Two of the SJML related projects are STO auto calibration, which I'll talk about first, where a convolutional neural network is used to self-calibrate AIA. And the other one that I'll talk about here is temperature maps of the solar atmosphere. So this is where we use a neural network to accelerate differential emission measure inversion. If you're not aware of what that is, I will quickly introduce it in the following slides. So let's look at the STO auto calibration result. So we know that the instruments degrade in space. So this is coming back to the degradation. What we see is that we fly sounding rocket flights to calibrate AIA because we know these filters degrade in space. And so while these are extremely helpful, the data is interpolated between successive flights. So in this work, Dos Santos et al. Use a convolutional neural network that takes either a single AIA channel or multiple channels and outputs the corresponding degradation factor or factors for the multi-channel version. This has been trained on, I think, 4 years of data up until Megs A switched off. And we have been able to learn how to go from the AIA images to figure out what the degradation factor is. So this notebook goes through reading and loading the STO AIA data, the SJML, before performing inference with a multi-channel model. With the inference performed, we create a degradation table and apply this to AIA data. So this figure shows the 304 angstrom channel. So this channel suffers the most degradation over time. Plotted on the same color scale, left to right, once a year from 2010 2020, we can see that if you just plot the number of counts that have come through SDO, it shows an apparent dimming of the sun over time. The bottom panel shows the ML corrected data using the ML auto calibration method. This is a really nice result, in my opinion, of how we can use machine learning to self-calibrate instrumentation in space. It doesn't remove the need for the initial calibration, obviously, because we needed to train this as a supervised problem. But I'd highly recommend checking this out if you're using SDO data. By default, the SDO ML data comes corrected with the Lockheed Martin calibration files, but this is a nice way of calibrating it in real time, and something that we're looking to use on another of our projects that I'll discuss in a bit. So the second project on Spaceml that I wanted to touch on is a method that uses deep learning to approximate and accelerate a known method for differential emission measure inversion. I'll try to quickly introduce the topic before showing the notebook. So as we discussed, SDO observes the sun in 6 optically thin extreme ultraviolet channels at a cadence of approximately 12 seconds and a resolution, I think, of 1 arc second. Here we show the 171 image left and the response function on the right. So 171 observes plasma at approximately 1 million Kelvin and is relatively isothermal compared to the other channels. Unfortunately, the majority of channels aren't isothermal, and some have substantial multi-thermal behavior, such in the blue channel there, which I think is 2 on 1. So what is the problem? Well, to map the temperature of the sun's corona, i.e. make maps of how much plasma exists in the corona at a given temperature, we need to first disentangle the multi-thermal response of the telescope from the multi-thermal nature of the corona itself. And this is the differential emission measure problem. More formally, we can write this as an integral equation, and the forward problem is relatively straightforward. With a known temperature distribution, we can determine what the counts in the SDO AIA would be. However, if we have the SDO AIA counts and want to determine that distribution, this is an ill-posed inverse problem. There are a large number of distributions that will satisfy the input data. So for all SDO AIA channels, the matrix formulation of this can be written as G equals K eta. And G is our observable, so it's an M tuple of SDO observations, so 6. K is the M by N matrix that represents the temperature response functions. And eta is the N tuple, so it has 18 temperatures, so you want to recover the temperature distribution over 18 temperature bins. From this formulation, a naive way to determine the DEM is to just invert K, right? If you take it to the other side, you'll just recover the distribution. However, due to the nature of the problem, it's at least a significant noise amplification. So what people have done is that they've tried to generate the differential emission measure using numerous mathematical techniques. 2 of them that are of interest are Tikhonov regularization, where you add regularization to the problem. So you add additional constraints to the problem when you're trying to go from the SDO observations to the differential emission measure. And then there's also basis pursuit that we'll talk about here. So in this code, essentially what you do is you define a dictionary of possible temperature components that can be added to create the solution. And we find a solution that tries to minimize the number of components. So the idea is that a large Gaussian would be a better fit than many very narrow Gaussian to the temperature distribution. And this is based on the concept of sparsity. So it's a very simple multi-dimensional regression problem. And one of the first examples that uses SGML. So you want to learn the mapping from SDO detector counts to the temperature distribution. We know that both X and Y have to be greater than 0. You can't have negative counts of the detector, and the amount of emission measure at a given temperature has to be greater than 0. Due to the high dynamic range, we apply square rooting of X and Y, and we know that the dimensions of X are less than the dimension of Y. So to demonstrate, this is the first demonstration of SGML, and I'll walk you through how this works. So how does DPM work? Well, we want to learn the mapping, as I've said, from 6 EUV values from this AIA channels to 18 temperature bins for every pixel in the set of images. We pose in this notebook, we pose it as a convolutional neural network with a kernel size of 1 by 1. And this just has, for this example, a single hidden layer. This is perhaps one of the most simple neural networks you can implement for this supervised learning problem. And because the images of SDO are 512 by 512, we have essentially 260,000 training examples in each the train, val, and test sets. We only use a single image for the train, val, and test sets, as it is a demonstration. But with the model defined, the notebook goes through loading the data, and we can then train. Here we train for 500 epochs. However, you could alter the epochs and learning rate. On a mid-range GPU, so we train it locally, but on a mid-range GPU on the Google Colab, it took about 4 seconds per epoch. We show the plots of the training loss and validation against epoch, and once the model is trained, you can then perform inference. What we see is that we see a 10 to the 4 times speed increase on basis per shoot. So essentially, we have a neural network now that is mimicking how basis per shoot works, but at a much higher speed. And that is super important because these are so calculating the differential emission measure is computationally intensive. And if we can do this much quicker, we can perform differential emission measure inversions as the data comes in. So finally, we also need to test our model, right? So here I'll concentrate on comparing the AIA observations, but there's a number of ways you could do this. You could compare the distribution from basis per shoot and the neural network. You could synthesize SDO Eve observations even and try and compare them, or you could just compare the mean DM. But I think for this example, comparing the SDO AIA itself shows kind of the importance of this method. So to synthesize the AIA observations, a really neat way of doing this, and the reason I like this notebook so much, is that you can just pose it as a 2D convolution. If you set the weights of the convolution to the SDO temperature response functions and the biases to 0, you have a very computationally efficient way of generating AIA observations from that original matrix K. So what do these look like, right? So we would hope that each row would be identical. And so the top row is the 171 angstrom. So this is pretty isothermal, around 1,000,000 Kelvin. So on the left is the SDO AIA observations. And the middle row is basis per shoot, so the code that we're trying to replicate with DPM. And on the right is DPM. We see that these are similar. So basis per shoot is very similar to the DPM solution. But specifically, we don't have the zeros in the solution that basis per shoot has. So basis per shoot has some issues where it will not converge on a solution for a given pixel. DPM gets around this by learning the mapping and can generate you a solution depending on how, so it could generate you a solution. The bottom row is 2 on 1, and I'll look at this closer. So what we see here is that if you zoom in, we emphasize the similarities and the zeros being removed. So what we obtain is a differential emission measure map for every pixel in the image, which cannot be obtained with DPM. So in addition to speeding up the method, we also recover solutions in every pixel. And here you can see a comparison of 171. So on the left, so the 171 is peaking at approximately 5.9 Kelvin, 10 to the 5.9, and compared to basis per shoot and DPM. So what we see is that these should be very similar because we're asking to just look at the 5.9 Kelvin solution. And yeah, so what we see is that the pixels are recovered where we don't in basis per shoot, but importantly, we recover similar values where basis per shoot fails to recover information. So the third and final project that I wanted to quickly mention is the deep learning virtual instrument for monitoring extreme ultraviolet spectral irradiance. So as we know, measurements of the extreme ultraviolet spectral irradiance are essential for understanding drivers of space weather. In this work, we used Sjml to learn a mapping from the EUV narrowband images to spectral irradiance measurements between 2010 and 2014. And this was prior to the time when the Eve MEGZA component ceased to operate. The best performing model is a CNN that, one, outperforms the physics-based differential emission measure approach that I discussed previously. And in this work, we yield an average relative errors of 1.6%. We are currently working with students at Carnegie Mellon to retrain this model, incorporating the SDO auto calibration work that I discussed earlier, as that is super important for this model. You need the calibrated data. So what we will be able to do is provide a live dashboard of synthetic Eve observations based on live SDO-ML auto-calibrated data. So I know this was perhaps a bit quick, but in the coming months, we are due to popular request, we're going to be working together with colleagues in Switzerland to build a PyTorch data loader for SGML data. And to summarize, SGML is a cleaned, curated data set covering 2010 to present. Version 2 is available on Spaceml, and there is a notebook in place to demo data access. Small subset is freely accessible to anyone who requires it. The full data set is available on request. You just fill in the form and you're granted access. And Spaceml provides examples of ML projects that use SGML, along with notebooks to reproduce the results. In the coming months, as I said, we'll build the data loader for SGML data. And on the right, I provide a number of references to the work that I've discussed here. And on, I guess I should, yeah, and thank you so much. I will play. Sorry. Yeah.
Thank you so much, Paul. That was a nice talk. If anybody from the audience, right, I think Divyendra has a question.
Hey, Paul, thank you very much for this nice talk, highlighting all the services that you're doing for the community. I think we really appreciate the fact that you're making this available for folks all around the world to use. I was just wondering if the people outside of this group who have made some contributions in terms of some algorithm development using SGO pipeline, are you open to sort of, assimilating them as part of this, in the sense that is it a sort of a, where you are looking at it like a community coordinated modeling center kind of thing, where you also assimilate jobs done by others, which might be useful for the community?
Totally, yeah. We'd love to bring together, basically what we want to demonstrate is how, we want to make science more reproducible. There's a problem with reproducibility, and I think it'd be great if people would love to upload their projects. I would say the person to get in contact with, I don't know if Vishal's online, but this
Vishal, I think, is right now in
he's in
the
Paris
workshop in Paris. Yes.
Yeah, so he has some work on there, but I think it'd be a great idea. Please contact me. So my email address is on the bottom here.
Okay, right.
But we'd love to have the code there. The idea is to demonstrate SGML and make it easy for people to reproduce results. I think I've struggled in the past I find some really cool project, but I can't get the code to work. And then you kind of just, it's like what do they call it? It's like the not invented here syndrome of, if it wasn't done here, we're going to just reproduce it. But it kind of, yeah. I'd love to be able to have more projects on there. And everything's on GitHub. And yeah.
Yeah, great. Please, I think this is a wonderful initiative. Thank you very much for highlighting this.
Thank you. Yeah, it's free. That's like the main thing. They want it to be free and easily accessible to people to use this data, because it's good data. Yeah, thank you.
Thanks.
If anybody from the audience has a question, you can unmute your mics and just ask.
Did I answer your question about the degradation?
I think yes. I mean, I don't understand why that happens, but yeah.
I think there's just some reaction to the. Sorry.
Yeah, I think there is. Please continue.
I was looking at the messages that popped up. I think there's some reaction that happens in the filters. I don't know why, but the filters that are used for observing EUV are also affected by that EUV emission. And so you don't have this problem with HMI, for example. And it depends on the channel. So you have different, depending on the channel of AIA, you have different degradation. So the one that I showed, which was 304, that's the most severe. And the problem we've seen is that people don't correct for it. And not correcting for it just adds more information that the neural network has to learn.
Right.
But yeah.
Okay. Yeah.
References. Yeah, so to answer the question about the reference sensor used to be Eve Megs-A, but that ceased operation in 2014, I think. So I think that's how it used to be done, was you'd use the EUV spectra. So you have the, so if I go back to the slide, So you would have you have the overlap. So I think that's how it was corrected in the past. But then once it stopped being observations here, sounding rocket flights had to be flown, I believe is what happened. So ideally, yeah, you would correct it. But one of the problems that we've seen is that because the flights are so infrequent, you then start adding, like, connecting points linearly. But really, it's not like that. The degradation kind of falls in a really interesting manner that I'm not sure anyone is really sure about how that happens. Otherwise, I would model it, I assume. But yeah. I know. If you have any questions, definitely feel free to reach out. I'm more than happy to help people use this data. And yeah, if you want to upload your presentation, if you want to upload work to Spaceml, feel free. Just let me know. We essentially have it all on GitHub, and it's really nice to bring stuff together. Yeah, thank you for your time.
Thank you so much, Paul. If we do not have any further questions from the audience, we can move ahead to the next talk.
Sounds
yeah, thank you so much. Yeah.
Thank you.
So we have Dr. Soumitra Hazra from UMass Lowell, and he's also a SSE alumnus, and he'll speak on distinguishing between flaring and non-flaring active regions. Soumitra, please take over.
Okay. Hi. Hi, can you hear us?
Yes, I can
Can
hear
you hear me? Okay.
Yeah, and you can see your screen. Yeah.
Okay, that's. Okay, so first thank Joshita for introducing me, and also I thank the organizers for giving me the opportunity to present this work. So today I am going to talk about the distinguishing between flaring and non-flaring active regions. So the solar flare and CME is basically the two biggest explosions in the solar system, and you see in the figure that there is a cartoon image of solar flare, and it impacts directly the Earth's magnetosphere and creates the geomagnetic disturbances. So if we want to predict the phase weather, we must have a clear understanding about the occurrence of solar flare and the CME. And solar flare is basically a sudden and intense storm, like tornado and cyclone in the earth. You can compare them with flare and CME in the solar system. So solar flare occurs when magnetic energy that has built up in the solar atmosphere is suddenly released. And these solar storms are the major reason for the disturbance in the phase weather. So we want to predict the solar flare here, and it is believed that the sunspots, which are basically a spot on the solar surface, that is the responsible for this kind of solar flare and CME. And there are different classes of solar flare. However, most intense is the X and M class flare. So, and these flares have significant impact on the phase climate. So, what do you want to predict here? We want to predict this possibility of this M and X class flare. So, there are different actually ways to predict the solar storm, like statistical way or MHD simulations and machine learning. So, here our approach is basically the machine learning techniques. And in machine learning technique, actually, there are two kinds of problem. One is the regression problem, and another is the classification problem. And as soon as we will see some problem, first we have to decide that what kind of problem we want to tackle. And in case of regression problem, one have to predict a number. Let's say we want to predict the solar cycle. Means we have to say that, okay, at cycle 25, this amount of sunspot will occur. Or let's say we want to predict the semi-timing or flare timing. So this is the kind of regression problem. And another problem is the classification problem. What we have to say, okay, this active region is going to flare and this active region is going to non-flare. So this is simply a classification problem. So as here we are focusing on the distinguishing between flaring and non-flaring region, so our problem is basically a classification problem. And when we decide that this is the classification problem, next step is we have to decide what kind of method we will use to do that. So in the machine learning literature, again, there is a two process. One is supervised learning and another is unsupervised learning to train the computer. Basically, you can compare this learning process to a human system, human also, that when a child borns, he is basically a black box. So later what happened, his teachers or parents teach him by showing different objects like mango and banana, this kind of thing. And after that teaching, child can take his own decision. So this is kind of a supervised way of teaching. And here you see that in the supervised learning, levels are given. Like when we train the computer, we already have the past information of the data. And in that data, there is already, we know that this active region gives us flare and this active region don't give us flare. So based on the past data, level data, we will train the computer. And after that, computer will take its own decision. So this method is the supervised learning. And another method is the unsupervised learning, because sometimes it is not possible to teach everything. So, but if we give some idea to the computer, or like if we give some idea to a child, and then he can take his own decision, like if we give computer the idea of distance, then also, even if computer don't know the levels, based on his idea on distance, he can actually classify. And that is the method of unsupervised learning. You see here, we don't provide that kind of levels, but in this method also, computer can classify the instances. So basically here, in our problem, we already have a past well-known data set where we know that this active region gives flare and this active region don't produce flares. So our problem is basically a problem of supervised learning. And in the standard machine learning pipeline, this is, so first we have to generate the data set. And after generating the data set, we have to do some pre-processing or feature extraction process. After that, we will apply the machine learning algorithm on this data set. And finally, we evaluate the results of our model. And if the result is good, we will employ them to predict. So this is basically the flow of supervised machine learning, that first we have to prepare the data. And after the preparation of data, we will divide the data set into testing and training. Let's say 70% for training and 30% for testing. And then we will train the computer based on the training data set with level or target output. And computer will learn this from this training data set using defined machine learning algorithms. And after the learning process is over, we will provide the testing data and computer will predict the target level or output automatically using his learning experience. And finally, we will compare computer predicted target output with the original target. And that will give us the accuracy of the model. And if the accuracy of the model is good, then our model is actually ready for the prediction purpose. So, as already in the previous talk, Paul discussed that HDO produces the lots of data for us. So, here we use the HDO HMI vector magnetogram data for our training of the computer. So, what we did, we first calculated different magnetic parameters like total unsigned current, helicity, Lorentz force, vertical current, magnetic free energy density. So there are lots of parameters that actually we calculated from the HDO HMI vector magnetogram data. And then we use these magnetic parameters for the training of the computer. So before doing this, first we studied some time evolution of flaring and non-flaring active regions. So what we did, we selected few active regions which gives us flare and few active regions which don't give us flare. And we compared them actually manually. So here you show this is the time evolution of the unsigned flux. And these blue dotted lines are actually the time when this active region actually gives flare. So you see that there is a lots of variation here, and sometimes flux decreases and sometimes flux increases. And basically it represents the phenomena of flux cancellation and flux emergence of the solar surface. And this is the unsigned vertical current, and this is the unsigned helicity, and this is the total photospheric magnetic free energy density. So in all cases, you see that there is lots of variation. And another interesting thing is that once flare starts happening in an active region, it keeps on flaring for some time. However, in the non-flaring case, you see that there are variations in all these parameters, but still it don't cause any flare. However, if you compare the values of unsigned flux and vertical current, all the values, you will see that all these values are much less in the non-flaring region compared to flaring region. And so what we have to do, we have to predict the flare. And every active region is the unique. So we have to find some unique clue which can distinguish actually this flaring region from the non-flaring one. So what we did, we wanted to train the computer by the time evolution of the magnetic parameters. So let's say flare happens at this time, T. So we go back some time, let's say L, it may be 24 hour or 48 hour. And then we take some time span during which actually time evolution of magnetic parameters takes place. And we train the computer by using this time evolution of the magnetic parameters. So, and that is basically because most of the previous studies, theoretical studies, suggest that the time evolution of magnetic parameters are the major factor for solar flare. So we think it is better to train the computer by using the time evolution. So now how we will use this time evolution part for the purpose of training? So what we did, we represent this multivariate time series using 8 summary statistics like mean, standard deviation, skewness, and kurtosis of the time series. And these are basically all statistical parameters. But yes, you can say that this is not the best way to represent a time series. However, we think that it is the simplest one. In all these cases, you see that there is no information of actually periodicity behavior. So maybe some Fourier series information will be much better. But here we use only this 8 summary statistics for the training purpose. And then next part is we have to choose the classifier. That there are different classifiers like logistic regression, support vector machine, neural network, and many. So here in this talk, I will mostly speak about the two types of classifier. Basically, the logistic regression, which is basically the one of the simplest classifier. In that classifier, what happens? You have a defined inputs like x1, x2, and xn. Then you have to just fit a logistic function into this data. And this function is a log of p by 1 minus p, whereas p is the probability of event occurrence. And if this term is positive, then the probability is more than 50%. And you can say, okay, this instances is positive. And this algorithm actually separates the classes by constructing a linear decision boundary. And another classifier I want to discuss here, that is basically the artificial neural network, or this is mainly the backbone of deep learning also. So here you see that it is basically the biological inspiration for the computation. And that's why one defined the neural network. And we know that in our human brain, there are lots of neurons. And in neurons, there are dendrites. Dendrite is basically captures the signal, and then there is a cell body. And what cell body do? Then cell body processes the signals like inference, infer the signals, and finally the product output is done by axon terminal, and it goes to some other neuron, and every neurons are interconnected, and that's the way our human brain works. So basically the neuron is the basic building blocks. Here in case of ANN, or the basic building block is artificial neuron, or the perceptron also called. So here also you see that there are different inputs like x0, x1, x2, and then like dendrite, we give here the inputs, and these are the weights W0, W1, W2. And now these weights is like inside the cell body like this. Here Wi, Xi, we sum over all these things, and we you can add a bias, and then pass to a activation function. And then the output is this will give you an output. So this is quite similar to the biological neuron, and that's why this neuron is called the artificial neuron, also called the perceptron. This is the basic building block. So in what happened in the neural network, that this kind of many artificial neurons also, we will also interconnect many artificial neurons to construct a neural network. So again, this is the simplified picture. You see that inputs and weights and summation and activation, and then it will go to a activation function to give the output. Now question is that how we will choose the best set of weights and bias for our problem, because we don't know that what is the value of W and what is the value of B. So question is whether neural network will choose this automatically or we have to choose. So what we do here, we initialize actually these weights and bias randomly. Okay, by some random number. And after that, what happened? This network will produce an output. And we already know the target output, so we can calculate the error. And this method is the forward propagation. So when the error is calculated, this error will be back propagated to adjust the weights and bias. And this method will continue until we get the desired result. So basically by the forward and backward propagation method, actually we can fix the best set of weights and bias. And here you see in the these are this blue color and the magenta color, all are basically the neurons, and within these neurons, this summation and activation kind of things taken place. And these neurons are actually interconnected with other neurons to generate the produce. And these are the input layers and these are the hidden layers too. And when there is two hidden layer or one hidden layer, we call them artificial neural network or neural network simply. Sometimes it's also called a multi-layer perceptron. But if there are more layers, then we call them deep learning. You see that in case of simple neural network, we have only one or two hidden layer. But if you have four or more than four, five, then we call this as a deep learning. And performance of deep learning actually improves with the amount of data. If your data is less, means then we can use some other methods like logistic regression or SVM. But like when we want to do image processing, like there are lots of pixels, so data amount is high. So deep learning is more useful there. And another advantage of deep learning is that you don't have to give them the features. Feature extraction is basically the automatic in deep learning. So no human intervention required. You have to just give the data, and deep learning will automatically extract features and you will give you the output. And after the choosing the classifier, we have to measure our performance. And basically the confusion matrix is the output. So this is basically consists of all of you know already: true positive, false negative, and true negative. True positive basically when the actual is positive and predicted is also positive. And true negative also the actually its negative instances, predicted is also negative. And based on this four parameter, you can construct different kind of parameters to measure the performance of your model, like accuracy, that is the total number of correct predictions made by the model over all kind of predictions made. And there are another precision equal. However, in our case, you see that the data set is imbalanced. Basically, the number of flying regions are much less compared to the non-flying region. So when the data set is imbalanced, then problem is that if you choose the accuracy as your performance measure, then problem is that if your model predicts all instances as non-flying, then also your accuracy will be very high. So this accuracy, precision, these measures are not actually very much accurate for the class imbalance problems. So people introduce different kind of performance measure for that, like Gilbert skill core, Hedges skill core, or the two skill statistics. And it has been shown earlier that this two skill statistics actually is independent on the class imbalance ratio. So two skill statistics is probably the perfect measure for our problem here. And so after that, so for the model, first we have to tackle the class imbalance, because as I said that flying regions are much less compared to non-flying. So there are different methods like oversampling techniques, undersampling techniques, or weighted techniques. So here we use the weighted techniques. So basically, in this techniques, we provide more weight to the classes which we aim to predict. So here we want to predict the flying classes. So we provide more weight to the flying classes from the non-flying one. And this is the result from our model. So you see that we have constructed the defined data sets with look 24 means it's 24 hour back, and we use the 12 hour of time evolution there. And in second case, we want to predict 24 hours before, and we use 24 hours of time evolution. But here we don't use any kind of time evolution in this data set. And again, in the fourth data set, we want to predict 12 hours before, and we use the 12 hours of time evolution. So you see, basically the THS, in all these cases, we got very good THS actually. And even when we don't use any kind of time evolution, like span is 0, then also we got the THS score about 0.86. So actually we don't know that whether time evolution is very much important for this kind of problems. It is probably that just, okay, if your active region is flaring, all the quantity values like unsigned flux magnetic parameter values are high, and in case of non-flying, it is very low. I think because of this, even if you use just one instance, it just based on the higher value and lower value, it separates the classes. It's probably. That's why probably the time evolution does not matter much in this case. And also we consider only the top 5 magnetic parameters. And in that case, we also got very good TSS value. So probably the only top few magnetic parameters is sufficient to produce a good model. And this is from our model of logistic regression. And if we use the multiplayer perceptron, basically the deep learning model, then also we got very good TSS value. So in summary, our model is actually able to distinguish the flaring and non-flaring regions in a quite better way. And then we select the best parameter. So for that, what we did, we take the time series of one parameter like unsigned flux or unsigned helicity, and we test what is the value of TSS there. And based on that, we find that this unsigned flux and total unsigned current helicity is the best. Also, the total unsigned vertical current have the capability to distinguish the best. However, if you notice the parameters, you find that all the total parameters are more valuable. And that actually suggests what I told earlier, that if you have the higher values of parameters, and in one case you have all lower value of parameters, that means the larger and complex active regions are more flare prone than the non-flaring one. And basically the extensive parameters are more valuable, whose value actually increases with the size. So in summary, what we did, we have performed a comparison study between the eruptive and non-eruptive active region in terms of the time evolution. And as it is not possible to do this manually, we use the machine learning techniques. And we find that it is possible to distinguish the flaring region from the non-flaring one with good accuracy. And although we don't find a critical magnetic parameter, like a unique parameter to distinguish all of them, but top few of them, like unsigned flux or current helicity, top few parameters have the best distinguishing capability. That's all. Hello? Hi.
Hello. Yeah. Is there somebody? Okay. So if you from the audience, if you have a question, you can unmute and ask. Yeah.
So, Shobhitra, this is Dipendu. Thank you for a nice talk. So what you are suggesting is this, that, you did this study based on parametric estimates and training. However, you're saying that a time series doesn't really increase the true scores that distinguish the flaring from the non-flaring classes. You're saying that single inputs, a single time magnogram or whatever inputs is enough. Is that what you're saying?
Yes.
Okay, all right.
Just to distinguish flaring region from the non-flaring one.
Right, that's good enough. The other
But
thing that
not
you
for
said,
the prediction purpose.
Sorry, can you repeat that again?
Means not for the flare prediction purpose. Suppose if one wants to separate flaring region from the non-flaring one,
Okay.
then just one instance of magnetogram is fine. And in
Okay.
my opinion, that in case of flaring region, you will get all the parameters have very high value, and in the non-flaring region, you will get all lower value. And based on that, actually, that's why these all machine learning algorithms are highly successful.
No.
However, when
Now
we
when you actually make predictions and calculate the true skill statistics of a prediction, are you
Yes.
saying that even there the time series are not important, or do you think the time series are important and do a better job?
Time
It was
series
not very clear to
actually,
me from your talk what you're saying. Can you clearly clarify it?
time series is not important in the purpose for distinguishing flaring and non-flaring region.
How about predicting whether an active region, given active region, is going to flare or not?
Then it is important.
Okay, and
But
is
that
this
is
something
a
that has been
totally
worked out in a paper that you referred to, or you can just send it to us?
actually till now I think nobody is highly successful in that. That is actually the time prediction of solar flare. In that case, time series is going to be important.
Okay, thanks.
But that's a totally different problem.
We have another question in the chat box from Hema Priya.
Okay.
What is the impact on the model on tuning to single metric TSS or GSS? Like in general, this is done at the cost of increased FP rate. Could you please elaborate on that?
Yes, actually the increasing of false positive actually more important. Like, I think in case of TSS actually independent of class imbalance. Okay, that's why TSS is important. But in case of GSS, if you see, we go to my presentation. So Gilbert's skill core, this is actually indicates the says its number of TP obtained by chance. Gilbert skill code has actually some effect of the class imbalance, means it's not fully independent of class imbalance. And so TSS in that sense is more important. But again, you have to check the confusion matrices, that what is the value of your TP, AP or FN or TN, because if it is better if you can reduce your false, means reducing false positive is good, but more better is if you can reduce the false negative here.
16th August.
Okay, so if you can reduce your false negative, then your model will be more good. So that's the aim. So in that sense, one can use TSS, or GSS is also, actually GSS has some dependence on the class imbalance. So is it clear?
Yes. Yeah. So
So
thank you so.
actually, one
Yeah.
have to reduce the false negative mainly.
Uh,
28th August.
okay. So there's another question from Ashwin. In summary, for cataloging the flaring and non-flaring events, time series does not have any effect in categorizing. But
Yeah.
for prediction, uh, predicting them, time evolution should be considered.
Yeah. Yes, that's correct. Because when we said that flaring region distinguish, we distinguish the flaring region from the non-flaring one. And if you apply the model, what will happen if there is active regions on the solar surface? It will give you the probability of flaring. Okay, so if an active region has higher values in all these cases now, your model will flag them as positive. So your model is actually not giving you the time for the flare.
Version to 9 June.
So if you want to predict that when exactly the flare is going to happen, then actually time evolution should be considered. Then time evolution is necessary because now you know that these activations are going to flare. Now when it is going to flare, when exact time, then the time evolution is necessary. But in this talk, actually, we focuses just on cataloging the flaring and non-flaring events.
Are there any further questions from the audience? I'm assuming there are no more questions. Thank you so much, Sjml, for that wonderful talk. So we have neared the end of this Spark workshop. I would request Professor Dibyendra Nandi to deliver the closing remarks.
Hey, yep, thank you very much to everybody, particularly the audience who hung on with us over the last few days at different times. We could get to juggle folks from different time zones. So sometimes we had talks in the morning sessions, sometimes we had talks in the evening session, and we had this uh, hands-on tutorial running in the afternoon sessions. This was put together by a bunch of people. I acknowledged them in the beginning. Let me not name them again, but thank you very much to the local organizing committee, which was led by Shubhodip, and to everybody else who contributed to this meeting, as well as the speakers who delivered wonderful talks. This is quite exciting and diverse meeting. I would also like to acknowledge the sponsorship from the Spark program of the Ministry of Education of the Government of India for making this workshop possible. With that, may I request all of you to maybe put your videos on so that we can take one last group picture and add on to the picture that we took on the first or the second day. So if you are there, could you just put your videos on for a group picture? Chitradeep, may I request you to take a group picture, please? And can you confirm after taking a picture? I'll also try to take it in YouTube, a screenshot.
Yeah, that access is solar flare and CME, basically the two biggest explosions in the solar system.
Since it's a little backlogged, I'll try to take it in YouTube, a screenshot. Okay, so I guess we are all ready now. Chitradeep, can you confirm after you've taken a screenshot for us?
Yes, we got a screenshot.
Can you take one more, just so that? Okay, so I guess we are all ready now. Chitradeep, can you confirm after you've taken a? Okay.
Yes, we got another
Done.
one. Yeah.
All right, thanks. Thanks everybody for attending. And I think what we'll do now is once the lectures are all online, we'll send all the participants and the speakers the links to the lectures, the YouTube lectures, so that you can go through them at a slower pace because it was very intense, particularly the tutorials in the afternoon. And you have access to the lectures as well. Wish you all good night, good morning, wherever you are. And thank you again for your participation. Bye-bye.